In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice, a flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einsteinian demons. These creatures thrived in the distortion of space-time, causing chaos and disruption. The world needed a hero, and Miller was ready to answer the call. With his flute in...
Made it to Discord.
Yay!
Yo, welcome Taylor. Hello and welcome everyone. This is Aether Cosmology or Aether Roundtable number 55. We're going to be doing bottom-up obstruction presented by Shane St. Pierre. Shane, whenever you're ready, sir, take it away.
Thanks, man. Nice. So we're going to do pretty much a focused presentation on specifically the disappearance of objects bottom up on a flat plane. Compare it to how they have mystiqued it for Earth curvature, even in light of all the empirical evidence for optical limits and Rayleigh's criterion and the limit of vision and wavelengths and everything that goes into optical limits and that has been verified and measured and empiricized. They ignore all that and just claim that every effect near the horizon is curvature, and that's how the Earth is curved. It's kind of crazy, but we're going to get into it a little bit. Right, we're going to start with the eye. There really could be a whole presentation on the eye and vision and how it works and how we magically evolved to have this ridiculously complex system to perceive and analyze the world around us, but we're not going to do that.
Maybe not much. Sure.
Hey, Taylor, punch the old mute button there.
Yeah, welcome, Taylor. We figured that out. So you can go to a whole presentation on the parts of the eye, but we're not going to do that. We're going to kind of buzz through. Just know that this is a spherical way to perceive a linear world, right? And the way that you perceive light and the way that you interact with this coming in this way is going to be important. So we're probably going to focus on, I would say, the lens, the iris, and the cornea, I would say. So if you look at these, all the parts laid out, right? The iris controls the size of the pupil and the amount of light. If you look at the lens, it's behind the iris and it focuses the light onto the retina by changing its shape through accommodation. Now there's two inversions going on here as well, but we'll get into that in the next slide. And then you have over here the retina, right? That converts light into electrical signals which are sent to the brain via the optic nerve, and also the stage of the final inversion of all perceived information. So next, we'll look at a quick video and explaining exactly how that works.
Inside the eye are various structures working together to create an image the brain can understand. Among these are the cornea, a clear dome-like structure covering the iris or colored part of the eye, the lens directly below it, and the retina, which lines the back of the eye. The retina consists of thin layers of light-sensitive tissue. This candle can help us understand how the eye captures images and then sends them to the brain. First, the candlelight passes through the cornea. As it does, it's bent, or refracted, onto the lens. As the light passes through the lens, it's bent a second time. Finally, it arrives at the retina, where an image is formed. This double bending, though, has reversed the image and turned it upside down. If that was the end of the story, the world would always appear upside down. Fortunately, the image is turned right side up, in the brain. Before that can happen, the image needs to travel as impulses along the optic nerve and enter the brain's occipital lobe. When the image forms there, it regains its proper perspective.
Right, so just a quick basic 1, 2, 3 on how the eyeball works, or a quick basic 1, 2, 3 on how we use spherical geometry to perceive a linear world, or a set of projective geometry, which is how we're going to go forward and analyze how we're seeing and what we're seeing. And I think it's important to see where we're coming from and the basic geometries involved, so that when we're talking about what we see and how we see it, everyone is fully clear on how we're doing that, right? So projective geometry is essentially what we're going to deal with in terms of perspective. When we're looking at, say, how to model an eye, we would do it like this, essentially. We'd be able to move it around. There we go. So when we're talking about observation angles, this is what we're talking about, the angles at which the light supposedly enters the eye. And you can see that these are related angles as one gets, right? They have the same angular relationship. They maintain a proportionality. If this is an eyeball and this is the image that we were just looking at, here's how it gets entered into the eye through this varying cone, right? Notice we can't make this very big. We can only make it 180 degrees. We can only go about this wide. This is the maximum of your visual cone, but we'll cover that in a little bit. But the main point is that we're going to be modeling and talking about the way we see the world and modeling it in projective geometry and lines of perspective and orthogonal and transverse lines. So we're going to be very clear of what we're seeing and what part of it we're seeing. So this is how we're going to go forward. If we look at this, this is a basic demonstration of how the eye works and how we're going to use spherical geometry for planar representation. So we're observing a linear world through our oculars in the SpaceAudits dialect, meaning through your eyeballs, right? Through your spherical eyeballs, which meaning the way that the vision works with the subtending and the absorption of light and the inversion of images and the translation back to the optic nerve means that you have this limited surface area to work with. And we know that we see that because that's, what all lenses are based on. That's what focal length is based on, the base of this part of the eye as well. We'll get into that in a little bit. But if we think about it as a lens, right, and looking at a block, we got 2 light rays are sent to our eye. And this is what we've been modeling, and this is the basic structure we're going to have going forward. Now, what it's emulating is essentially this, right? Our azimuthal grid of vision portrayed on an orthogonal sort of left to right axis, right? If you're a person here, you're looking out at the world, you can only see this much of the world. And in fact, if you're thinking about the whole world, you can only see about half of the world, right? The one hemispherical view you have of the celestial sky at any given point. But talking just about viewing the horizon at, say, your eye level, right? This is how you would view it. You have these subtending angles. It comes out in a spherical hemisphere. This is the same thing looking the other way. This is what we're going to be modeling orthogonally as we go forward. Essentially this, and this is the whole argument. If you saw this meme and you understood it, you would understand the whole argument and the crux of the argument putting forward. But I didn't when I first saw it. I just knew that it was the right answer, and I couldn't articulate quite how it was the right answer, why it was explaining anything or anything like that. But we're going to get into this. I put over here the cone of vision, which is basically a representation of a 3D perspective of what this guy would see at any given point. And over here we have the Vieth-Muller construct with the various ways that projective geometry could be transcribed there, with the sort of a sliding scale where we can do depth and far and near sight, and we can give it different types of geometry as we've done in other presentations. But talking about the horizon, so we'll get back to how we're seeing it, how we're using our oculars to perceive the world around us, right? We have a fixed viewpoint, we have visual rays, we have this angle we're going to be talking about a lot. This is all part of the visual cone, essentially a 90-degree cone from anywhere you're looking, right? So it extends from the eye, and the outer limits of the cone essentially are your field of view. So when you're talking about field of view, this is what it's referencing. Most people know field of view from video games and just add an adjusting slider in your favorite first-person shooter. You can see more of the field if you slide it over, right? That's why it's said to give you a competitive advantage. If you adjust your field of view, you can see more of the screen. You therefore are more aware and you're more able to make strategic decisions. So that the same is true with all optics, actually. Frame of view in optics is actually very important. But when we're talking about, again, how we see objects, we have our eye, we have light. All light that we see is reflected, as we know, reflected off objects, even in the heliocentric model, as it's traveling 93 million miles in perfectly parallel light rays. It is actually reflecting off of anything in the Earth's atmosphere before you see it. So we don't have to argue where it comes from, but we do know that we really don't see it till it's reflected, essentially. And this is how we're looking at the reflected rays coming into the eye. Now, when we talk about the comparison of angles, we know that there's an inversion point, right? We know that back over here, we see an inversion. This is entered into the eyeball, inverted, and then inverted again on the back. So we know that these angles are proportional. Essentially, we know that they're equal. The angular size of the object projected into the eye equals the angular size of the viewed object, meaning these are all equal. These are all equal angles. So we can use that in our observations and our measurements and comparisons and deductions, I would say. When we're going forward with angular size, we should be aware of the main factors that would affect angular size when we're doing experiments and making observations, and especially when we're trying to prove or disprove Earth curvature, right? This is going to be a big factor in any optic observation, so we should be able to quantify it and be aware of the different ways it can affect your results. So majorly distance. Distance affects angular size. The further these pairs of lines are away from you, the bigger the angular size will be, right? So the closer, the further away you get, the smaller the angular size becomes. Essentially, this is what this is showing. You affect the angle. The angle would also affect the angular size, meaning as you spin this, you get a different view and a different proportionate length of this line that is mimicked over here. Right, so the absolute line is constant, but an angular size would shrink according to the angle. So we've subtended these, we've twisted them a little bit. They're under torsion. We now see that the same red line looks to be a little bit longer, right? This is the line, and then this is the same line. So we're saying that one of the contributing factors that would affect the angular size of objects, along with distance, is angle. So in changing the angle of your view. The last one I would say would be height. Height affects angular size. So the height at which you're viewing an object would affect the angular size at which it appears. I think that one's pretty self-explanatory. If we try to apply it quick to a real-world observation, it's really just, we're really talking about Rayleigh's criterion here, but we'll just reduce it to, angular separation is the angular distance between 2 points of light, right? So when these 2 points are distinct, we can see them, and this is the angular separation we're talking about, seeing them. When they merge, they become one, right? Or when the Rayleigh disks become one disk, they become indistinguished from the other. Therefore, they're unresolvable, and then that's the limit of the actual angular convergence. So when we're talking about the angular resolution, we always say it's 0.02 degrees. Everyone says it a lot. What does it actually mean? Well, it has to do with a degree of visual acuity, meaning your ability to resolve things in the real world at real life distances. You have things like point acuity, grading acuity, stereo acuity. The whole point is there's different gradations of angular resolution limits based on the limits of the human organic eye or lenses based on it, for it to resolve objects and information at a certain level. If you think about it in a computer, in a modern age level, there's only a certain number of pixels you can have on a screen, and a pixel can only represent so much information before it gets lost. So if we're talking about anything smaller than the limit that we previously described as 0.02 degrees would be invisible. Is it there? Sure. Are you able to resolve it? No. So if it's unresolvable, it's synonymous with invisible. So the outer bonds of the cone here would merge together directly on the retina. We went over how that works. The basic practical application of what we're laying down here would be something like this right over here. If we're talking about how can you show what the resolving power of an eye or optics means or what it is, you would look at these little figures, and you can it says show this up to the class, right? No one beyond 4 meters can raise their hand because they can't identify the pattern at a certain distance. If you look at over here, they've changed that a bit to the pattern, we're meaning that they can tell you that a fraction limit would be observed at a different angle for the different limit. So you should be able to see the gray square over here. The distance would be definitely integral in determining this, but the point is there's a definite distance at which things become unresolvable to any form of optics, and it's baked into linear perspective, right? If we look at this basic image of breaking down a real-world observation into orthogonal and transverse lines over here, the squares, and we have the basic eye line, you say 50% above,
Shane?
50% below. Yo.
Your YouTube is having a hard time hearing you. They want you to.
Yep, got it.
Okay, thank you.
Thank you. So basically looking down the hallway, we're going to be kind of breaking down all the aspects of this going forward, but it's a basic description of the orthogonal lines are nearly horizontal at the horizon, and the visible floor represents 50% of the visual field, meaning your eye line is right on the horizon. If you took a camera and put it on the floor, this is what you'd expect to see. That's very close to the ground level, right? So that's why you get this sort of broken up perspective. If we look at what we were talking about before, we're talking about putting an eyeball at the eye line, right? And you have, say, different angles, but above and below, and you have to have these angles decrease proportionately for them to disappear proportionally. The only way you can see them disappear at the top and the bottom diminishing at the same rate is if these angles are diminished proportionately. This is all this is saying, right? It says the top remains, the bottom remains lost because you have a differential for the floor or the ceiling compression. It's talking about the compression of these angles as they're reflecting off the object, coming into the pupil and hitting the back of the eye to be analyzed and inverted. So the angle at which this is entering the eye is compressed, meaning these are equal, right? If they're not equal, then they will compress unequally. if we think about Rayleigh's criterion as we did before, there's a Rayleigh's, I think they're, what do they call them? The discs, whatever, the example for which things become unresolvable and into one. So, fully resolved, distinct objects and discs you can see over here, just about to be just resolved over here. They're about merging. They're almost indistinct, but they are kind of distinct. And then over here, they've merged together. They become one. They're unresolved completely. We're going to take this concept and we're going to apply it a little bit differently into how we see objects. But first, let's just, again, set the baseline here for how we use the eye to see things in the real world. We went over this a little bit, but to reiterate it, right, an object never really disappears until all the angles are reduced to zero, or until the thing is absolutely unresolvable, or until the top sets into the horizon. So if we look at how we would apply the Rayleigh's criterion to an object, if we just use, say, a 6-foot observer and you have a regular angle to the ground, if the line of sight crosses at 3.25 miles. We already know that based on other geometry as well. But if we're looking above and we're looking, say, at a space of ground, and we have these 2 points. Now, again, we're going to remember Rayleigh's criterion. We're going to use these 2 points as representations of our visual field. And we're going to see when they become unresolvable and when they merge together. And we're going to look at what that represents. So points D and E will visually merge, and then nothing is viewable in between the points. Now, we know in the real world, this represents a real world amount of physical distance between these 2 points, but when they become merged via the limit of your angular resolution, then the information displayed here will be lost to you. It will become unresolvable. Now, if we change it a little bit, the angle didn't change, but the amount of information here did change, right? The points merge, the bottom being in that space disappears, it becomes unresolved. We just have, this is just a bottom representation of your orthogonal viewing cone, and we're going to look at what happens with, let's say, a building, which is caught in this information with its 2 points being unresolved, or resolvable over here, unresolved over here. So we're going to go into that a little bit more, but let's also take a look at optics. When we're talking about viewpoint, perspective, angles, we're talking about mostly focal length and aperture we're going to get into. So widening an aperture increases angular resolution, right? Narrowing an aperture would decrease angular resolution. Shortening a focal length would create more depth of field, and shortening a focal length, lengthening a focal length creates more depth of field, my bad, and shortening a focal length, squishes the depth of field. And this is an example of what that would do just from changing the viewpoint with a different perspective. So when we start to get into analyzing, is the Earth curving because this mountain that I know a height is below the shoulder of a person in my frame, is that really a good argument, is what we're going to get into. And we're going to see how maybe we can take other empirical measurements that would be more trustworthy at certain distances. So here's a breakdown of, that orthogonal sort of viewing cone in a perspective view now with, different markings at what a change in focal length and depth would be, right? So 3 meters, 3 meters, 3 meters. This is showing you that these are increasing proportionately to the distance, right? So if you drew lines in the real world, as we will soon, you'll see that this will hold up in almost every circumstance. Now, again, we're going to get to focal length. This is just an example of what different focal lengths would be: 105 millimeters, 105, 50, 24, 35. These change drastically between them. You can see in this one, you can't even tell that there's a second object over here. The frame of a field is so big that you can't see it. If we put it in a other real world life observation, right, the person here can be seen to be above the objects over here and below objects over here. It's a little strange. It's the same person, right? Does the Earth curve more over here now that the tree is below? Or I know this tree is 6 feet. What's going on, guys? Well, you're just changing the focal length. And again, can be drastic. It's just, again, widening the aperture increases angular resolution going in. Narrowing decreases angular resolution. And again, lengthening the focal length creates more depth of field. So way back here, right? More depth. Shortening focal length squishes all your depth of field. So keeping those functions of optics and limits in mind, let's go back to our example for what becomes unresolvable and when things become squished, so to speak. And again, so we have it fixed over here, and the outer triangle is at the fixed field of view, and the inner triangle is essentially fixed at the angular resolution limit. So over here, these are the 2 points we're going to be looking at, and again, resolved, unresolved, merged, right? So fully resolved, merged, completely completely unresolved. So we're going to have information over here displayed equally in proportion to this angle again for the difference between the observer height and the ground plane. But when points D and E visually merge, then nothing is viewable in between the points, meaning you've lost all the information for your eye to interpret based on the light reflecting off this object now has been lost to you. Doesn't mean that the Earth is curved. It means that a certain proportion of it is now no longer resolvable based on the optics of the limits of your eye and or lens that you're viewing it from. Now, we just simply cannot perceive the missing space. These 2 points have become unresolvable. They've merged down together. They merged with ground distance and they can merge together. When we say equal angles can disappear equally, but unequal angles must disappear unequally, I think this is a really good representation of what I'm talking about. So let's see. If we put this, go back like 50. Right here. So, yeah, this one. Away. Come on, man. Let me click on my slide me button. I put it right there. You know what? I don't need it. Screw you, slide me button. It's fine. We don't need it. So unequal angle. So if my observer height was exactly equal between the top horizon and the bottom horizon, then the angles would disappear equally, meaning they would be able to disappear the top proportionate with the bottom. That's never how you're viewing the horizon. You're always viewing the horizon something like this, where the angle on the bottom is much steeper than the angle on the bottom. Therefore, this compresses at a different rate than this compresses, and it has to be proportionate and equal. And that's how you get the bottom-up disappearance. So if we're talking about how we're going to lose information in a bottom-up obstruction, we should first kind of lay down the visual field one more time and go over these lines of perspective. So most of this, all these images was taken from a video called Angular Resolution in Our World on Life is Short. Most of the following visuals will definitely be coming from, but we are going to watch a quick little 7-minute stint of the best, I think, breakdown of how orthogonal transversal lines would explain perfectly the vanishing line, the horizon, the vanishing point, the height of objects, how things are perceived, the depth of field you have, and how things you perceive in a tunnel. I think he does a really good job. So let's see if we can't get into that. But what he's going to be going over is essentially like this right here. All right, this is the main presentation. Again, this is the eyeball. Here are the light rays becoming off of these various objects. And the basic example is just a tunnel so that we have a limit on our field of top and bottom view. So we can really accentuate the differences between the top limit and the bottom limit because it'll be easier in a tunnel. And then when we go into the real world, it'll make more sense. So yeah, this is going to deal with the eye and the aperture height of the observer so that we're no longer perfectly positioned in the center of the corridor. So this is where the real world observations start to take shape. And we're taking an orthographic side view of an object down a hallway. Right. So as our angles change, the information at the top is expanded above our eye line and the information below is compressed. So if we remember the angles we just showed you, the one over here was much bigger, the one over here was much smaller. So those proportionate angles must decrease proportionately for us to get top and bottom disappearance equally, which they are not. So they certainly will not. We'll get a much greater disappearance of the bottom than we will the top. That'll be the prediction that we're going to see. If we think about it like this, we have a sort of 2 hallways being observed, right? And we have what you would see with an observer height very low to the ground where you normally see the horizon. And this is in a building or a house. You have a top ceiling, you have a floor and a ceiling, and they're not super ridiculously far away, so you can sort of see the difference. Now, if you just draw regular angles with a ruler about what you're seeing in the perspective grid, right, and you take account for the depth of field and you draw, you'll see that the angles compressing to, say, this point from the top are much different than from the bottom. From the bottom, we have a much shorter way to go. They're all much more compact than they are up here. And this is the compression that's going to cause bottom-up obstruction when you're looking at great distances, when you're seeing objects become unresolved at the slower rate starting from the bottom. And that's all that we're going to be seeing. So
we can look at our bottle example the same way. The bottle is still the same bottle. It's just viewed at a different compression rate.
So he's talking about this example over here where you have what I just laid out, but in real world, a line of bottles, and you have this line right in the middle, which would lead to top and bottom disappearance exactly proportionally equal, because that's what you would see if your eye was right in the middle. This is a more realistic observation of the same scenario we're about to mimic what would happen at normal eye level for a regular observer, for things at the beach, for things down a hallway, for any real life observation. And this is a cutout representation of the same over here. So this is a 3D representation of what you have right in the middle. And here's a low a representation of the eye more close to the horizon with the same view on the same models in real life.
So you can see how the eye line is in the middle of the bottle.
Yo.
It's hard to hear the video. It's very quiet for me.
Do you have your audio turned up? Because it sounds fine for me, but it's at 100%.
Okay, my bad. I
good.
guess anything.
On the image on the left, but the eye line is moved down towards the lower half of the bottle with the image on the right, but the bottle is still the same bottle height. Also note here, if you go to the right side perspective view, you can see how those lower transversal lines are very close to each other, how the upper transversal lines are much further apart, whereas on the left perspective view, they were all equally proportional to one another. Again, this is a function of your observer height. It's going to move your horizon line in or out, depending on the expansion and compression rate of those angles. So with a lowered eye height, we can see that if an object starts out below our eye line, it still remains there throughout and maintains its relative proportion to itself.
This is where the Globers try to trip everyone up. They're like, well, I know that this height, right? This height of my mountain and my shoulder and this sign are all equal. So when I get this far away, I know that this mountain is obstructed. Where'd the bottom of the mountain go? Right? That's always their argument. And we should always argue that, again, the same thing is true for when you're equal between the top and the bottom. They would increase and decrease equally, right? You'd see them decrease in the same proportion. But that's not what would happen at the bottom. Sure, things that are below the horizon stay below the horizon. That's absolutely true, and inversely true. If it's above, it would stay above. But saving the changes in focal length that we viewed before, which actually will definitely change those distances and heights. But other than that, things below the horizon will stay below, and things above will definitely stay above. So that they definitely try to trip you up with that.
Here's our box moving away from us, and we've got it very close to the eye line starting out. But you'll see it never goes above the eye line. It is always below the eye line. It just gets smaller and smaller. Hopefully that makes sense. Look at, if you also note, it's stratified along these potential orthogonal lines. All right, now we'll extend the object's height so that it starts out with some aspects of it above our eye line, but most of it below. So now this object is a little bit bigger. It's in front of us. It's now partially above our eye line and partially below when it starts out. As the object gets further and further away, the aspects above the eye line will compress at a different rate to the aspects below. It will appear to be a more dramatic change at the bottom, because more of the bottom of the object was below the eye line to begin with. So again, just take out some rectangles, stratify them along the orthogonal lines for their rate of ascent and descent along some of the orthogonal lines, like I said, and you will see the effect. So you can see here in the bottom left, those are the rectangles that I pulled out from the perspective view in a central perspective view, and then you just move the corners so that they stratify themselves along the orthogonal lines, which I outlined here in black. And you can animate them if you want, and you can push them off into the distance or make them come out to you as the observer. Either way, they will maintain their relative proportion above and below the eye line throughout the entire way. Let's reverse things now with most of the object above our eye line, like if we were about 6 feet off the water and looking at a large boat traveling straight away. And again, it starts off a little bit to our left. If you look closely at the diagram, you'll see that the bottom of the object is approaching the vanishing line or horizon. And at a certain point, as the object near this line, the angle is simply too compressed. You'll see down there at the bottom that the blue outlines of our rectangle start to merge along the bottom, and we go from distinct lines to a single kind of blurred merged line. Meanwhile, the top of the object still has distinguishable lines. We can count these rectangles much more easily. The bottom information is being lost as an object moves straight away from us along a plane. So again, I can blow up this image here, and you can see it there on the lower right. The image integrity is somewhat lost at the bottom, while the lines are still distinct above the eye line. I can see the distinguishing lines above the eye line of that object. I can no longer distinguish them below. As we'll see, the compressed angles below the eye line have proportionately expanded angles paired above. So as one compresses, the other expands. Keep that in mind. Or as I move left and compress the left angles, the angles on the right expand, so on and so forth. Also, for an exceedingly tall object, the aspects below the eye line are essentially negligible in comparison to their total height. So they stratify along the horizon line. Like if I was looking at a mountain exceedingly tall, way higher than 6 feet of the observer, let's say, you can essentially view it as being all above the eye line, all along the horizon line. So again, also objects, they descend at a rate commensurate with their pairing below the eye line. So again, if I compress the lower angles, that eye line or that orthogonal line is going to become more shallow, but at the same time, the orthogonal line that is paired above will descend at a higher rate. So again, if close to the ground, the descent rate is steep. If higher up, it's more shallow or gradual. So in the orthogonal view here on the left, these mountains would represent the same height if I observe them that way in that side-on orthographic representation. But they are seen below here in a one-point perspective, and so they therefore must diminish in size according to the transversal lines. I could replace a 4,000-foot mountain with a 4-foot car parked at different distances, and it is the same phenomenon. I would just be lower to the ground relative to the car to view it this way, and put my horizon line along the lower edge of the wheel, and it would be the same exact thing. The rate at which they diminish is linear within a fixed perspective. In other words, double the distance, half the size, triple the distance, 1/3 the size, and so forth. We can reverse some of the near and far objects, keeping them according to their transversal lines, and we start to see a typical panorama form with 6 equally sized mountains. The 3 on the left are in a straight line, but they are converging right. The 3 on the right are not in a straight line, but have the same heights at the same distances as the ones on the left. We could add in some clouds, and some different mountain heights here and there, and you can stratify them according to these orthogonal and transversal lines in the same ways. And this is how we see the world.
Man, that little clip is like the coolest clip from that whole video that I've seen. But it's a 3.5-hour presentation on pretty much perspective on how you view everything, and it's definitely worth it. But I pulled that clip out of it. I also pulled this little visual kind of amalgamation from it as well, when it's kind of just emulating view and orthogonal lines and how transversal lines would dictate perspective-induced height, and the height of objects always obeying this, and orthogonal lines meaning that, you know, depth perception and how things would appear to get small. It's kind of a de facto expert way to show it. I need to show this again, but I can't do it because it's not going to slide me. Oh, did I slide me? I think I might have to. Yeah, hold on. Ready? Am I still presenting? Yeah, I'm good, right? Discord's good? Okay.
Yep.
Yep,
Solid.
looks good.
All right. On the fly change is going well. Now I should be able to manipulate the thing. Yay. All right, cool. Now, my GeoGebra model works with Canva. So essentially what I'm modeling is like an eye level directly equidistant between the top and the bottom horizon, right? And that's what you'd get. It would only at this point would it decrease equally. But really what you're getting is something more like this. And this is definitely more akin to an eye level almost above the horizon with the skybox way over here, that much further away from you. I thought that was a really good visual representation of what those angles mean, and especially because we've said it a bunch of times, equal angles can disappear equally, unequal angles cannot, and they are very and vastly unequal. So
That's a
again,
very
just
nice
modeling it over here.
representation.
I did
I'm
spend
glad-
30 seconds to fix it.
I'm glad you went back and fixed it. That was great.
Right, because then we can have this model over here, and this is again the perfect pink and blue, perfect equidistant distribution. The eye level is right in the middle, but not in the case over here. And this is sort of the proportionate linear information loss. Like it says, the amount of distance is proportional to the height loss in a linear relationship. But as it's based on optics, and as we've done different presentations on optics before, I think it would probably more resemble a logarithmic relationship, because at that point it'd be linear for a significant portion, but there is a point over here where right before it becomes unresolvable, there's just a limit where it's not visible. And I think that would be the limit approaching infinity but not reaching it that a logarithmic scale would give us. So I agree with this up to a point, but it's kind of like how a parabolic representation of Red's curvature and the formula, say, of 8 inches per mile squared gets represented basically linear up to a certain amount of miles, right? Works the same. If we take what we've learned so far and try to apply it to a real world observation, now say in a building, and we're saying that the bottom angle is going to decrease quickly because the angle of ascent is steeper than it is for the top, right? Or in saying in a different way, the angle to the bottom is shallower than the angle to the top. The distance to the top is further than the bottom. If you look at it, it's something like this, all right, all the way up here, or really going all the way down here. If we take a look at, again, this the bottle example, but all mapped out, and then just trying to hammer it home here, guys. Trying to make a really, really basic point in many different ways, as many different ways as I can. So the information lost at the horizon. Now, again, we're losing information at the horizon the same here. The table isn't curved, but we're mimicking the effect of curvature inside on a totally flat surface just with optics. We're even diagramming it out with transversal and orthogonal lines to mimic depth perception, field of view, height of objects, and it's all perfectly matching. Note that when we drew it out, it looked perfect and mathematically symmetrical, and when we matched it to real-world observations, it maintained that proportionality and accuracy. That's crazy. And again, this was from a different example, but again, it's a real-world example of long distance with a camera height low to the horizon. I think this one is, what was it, a marker? I think it says, it doesn't matter. What it is the same object viewed so far away that the bottom of it is lost. The information there is not displayed to the back of your retina. The light is not reflected off of this tiny object and in line to get reflected into your retina to be able to make sense of it. It doesn't reach you. You can't see it. So if it doesn't reach you, then you can't make an image out of the information that your retina is trying to perceive. So it's lost. Literally, the bottom is lost. Now, is this driveway curved from the distance where the camera is based on this object? No, absolutely not. But if you change the viewing angle to almost the horizon, then the bottom of the object becomes invisible. And again, it's exactly because of this, right? Equal angles appear the same, unequal angles cannot. This is, I think, the best diagram. And again, I think during that clip on the Phone Booth podcast, I think I talked about this. If you haven't seen it, oh wait, I have one right here.
But why ships
Shout out to the
disappear
Phone Booth
bottom
lads.
up on a flat
Right?
right?
Yeah, man, right? That's a big thing that people always talk about.
Can you explain that to them?
Yeah, right. I think we have a pretty good explanation for it mathematically. To be honest, I have a debate that was supposed to be on this that I was gonna save this wonderful grade before and whip it out on this poor unsuspecting dude, but he's not worth it. So I'll just give it to you guys, and then we'll do a presentation on Tuesday where I'll perfect it and put it out with some nice analogous stuff. But it's specifically on bottom-up obstruction, and it's about the limit of optics, right? So when if your face is in the center of your perspective grid, then of course you have the equal distance on the top and the bottom. Things wouldn't disappear bottom up; they would disappear equally. Those equal angles would compress equally, and the top and the bottom would compress at an equal rate, right? So that makes sense. However, that's not how anyone views the horizon or any of the things that disappear. You're way on the close to the ground level. Your eyes almost on the ground level. So what you have there is a disparity between the angles now. So the shallower this angle becomes, the greater the other angle becomes. That's just to keep the same correspondence ratio that you have. So you have unequal angles compress unequally, equal angles compress equally. So if you're in the middle, they would have compressed equally, but you're not. You're at the bottom. So what happens is this is much shallower. The compression angle is much greater. You have compression from the bottom. Hence, bottom-up obstruction has an effect of optics on a flat plane. What do you guys think?
I think that's exact, and I'll say what I said before too. We're closer to the ground than we are the sky. That's basically how I sum it up, because I'm nowhere near as intelligent as you. So I'm just a dude who found out the Earth was flat and wants to share it with everybody, man.
Dude, I saw a meme that said that, and I went, "Oh shit, that's the reason." And then I told someone that, and they went, and I was like, "Fuck! All right, I gotta do something else." Everyone should definitely go check out the podcast. I had a good time. Those lads are really cool. So, if we're saying that we're mimicking the effect of what is supposed Earth curvature, but now we're saying it's an effect of optics, and we're using math to describe it, right? And we're saying that these angles are equally or not equal. We're saying that the ground distance is unequal, causing unequal bottom obstruction. Then, shouldn't we be able to reverse the effect and try to mimic top-down obstruction? Shouldn't we be able to have an experience or an optical phenomenon in this world where we should have the opposite circumstances should be true, where the top would disappear first, or we lose information from the top down because our field of view would be skewed that way? I wonder if we can find a real-life situation where that would be true. Well, if you look under a tall building, if you think about entering a tall building, and if you look up with a really narrow viewing angle and you start to get close to it, if you think about a person who's beyond the vanishing line, say at the very tallest floor, tippity top, leaning out a window, waving a flag. If you walk towards them, there'll be a point where you won't be able to see the person at this top window waving a flag. They will visually merge into the depth of field right over here from the top as you walk forward. You'll literally be giving the inverse effect of disappearance of bottom-up obstruction near the horizon. I thought that was so interesting and cool that I set out to replicate it. So if you look at a building in my nice neighborhood over here, and you walk towards it, you'll be able to see that the information that is viewable over here, say if you have 2 points based on a Rayleigh's criterion that are distinct and separate over here, then when you walk towards it, they will merge and become indistinct and unresolvable. Thus, we'll have information lost from the top down because it will be much closer to the skybox than it is the ground. What a wonderful demonstration of this. Again, I just put this information over here. This is what we have horizontally, but we're just going to flip this, right, and say that we're going to do it this way. We're going to lose information from the top as we approach it. I wonder if that's true. Let's see. Well, again, we're going to be mimicking this approach, right? We're going to be thinking that this is going to be happening from the top down now. Well, yeah. It exactly happens that way, it looks like. So that's the exact effect, if I'm not mistaken. If we go, and there it goes. So if the person is over here, we've lost information that was resolvable to us back here, is now no longer resolvable over here. They have merged the same way in which we get bottom-up obstruction at an eye level from the observer height right on the horizon. And again, we're just talking about how equal angles can appear the same and unequal angles cannot. That's essentially the whole point of the show. Let's see here. This is the whole video, I think, right? Starting in, walking over. Just taking with my phone so it's not super steady. But right over here, all lost. Information can't be seen. The top floor is now indistinct. It's become merged. It's compressed. Whatever you want to say to describe it, the information that was here is now gone. It is not resolvable to me. So, is this building curved? Or is the same optical effect that we see as bottom-up obstruction happening in reverse from the top? You guys decide, right? As they say. But again, there's another visual representation of how we're going to look at it, right? If we have all these balls, this decreasing in size equally, and we have an eye in the middle, then we see that anything resolved past here is unresolvable. So we can't see in this square, and we can't see beyond these. And they, of course, disappear equally, right? Same size, same size, same size. Again, if you bring your eye down to the horizon at the eye level where you make observations, you have the same situation, the same balls. You see that they are very unequal to start, right? Much bigger, much smaller. Kind of the same size. Much smaller, much bigger. Non-existent bigger. So the compression rate of these balls is much different than the compression rate of these balls. They are equally paced along the observer height. That's just another way to think about the same thing. And this is another representation sort of with the breakdown with the orthogonal and the transverse lines governing depth perception, depth and size relatively and proportionally increasing. This is the same orthogonal sort of side view of what you would see in perspective over here. So he's saying that the angle, so theta, would be when the thing becomes unresolvable is met from my lower observer height and sets into my lower horizon, which is now closer in that angle over here. It says information above the eye line, the descent rate is steeper, but less of an angular compression rate. So all the things that we've been saying so far. Let's put it into, say, another real world application and talk about the sun. How does the sun set on flat Earth, guys? If the Earth was flat, it would never be nighttime. Am I right? Man. No, the sun definitely sets. It definitely follows a law of optics, and when it becomes unresolvable, you too can no longer see it. It does appear to set right into the horizon, and it recedes bottom up as your eye limit and the skybox are at vastly different angles, and the lower angle is compressing much greater rate than the top. That is why the sun disappears bottom up in a nutsack, I think. So it descends into the vanishing line quickly rather than maintaining a relatively constant resolution angle as it travels. Side note, if you get a really good camera and you look at it, the sun will hang here for a little while before it goes dip because it's actually pushing through the last deck of atmospheric opacity before it becomes unresolvable. It's not actually sinking, it's pushing through. So if it was sinking, it would maintain rate constantly because it always sits and then waits at the horizon and then waits some more. And then poof, disappears sometimes. If you wait, it'll just poof, disappear right out. But if we're looking for a diffraction limited system, we're actually looking at real optics with the sun. This is what's happening. The diffraction limit is causing us to not see the sun anymore, essentially. All of the optics that we create are based on the human eye, so this is not just going to be limited to the human eyeball. Now, again, if we visualize the sun, we're going to expand and compress at different rates, and it's going to be the same exact situation. So put it in a real world situation. Let's say we had a really flat warehouse, right? And a sun on a stick that we linearly moved to the end of the warehouse until the sun on the stick became unresolvable at a linear rate by which we lost the bottom of the object first as the angles to the top increase rate. Oh, but look at that. It's exactly as we thought it would be. What a prediction. And if it was in reverse, you'd expect it to come back as a sunset, rising, right? Got a little stuck there. But now it's dark. It's dark, the sun is gone, there's no light. The guy is still there, the sun is still there, but it sets, right? It looks exactly like this. To put it in another real world situation, we can use lasers in a warehouse. You can use lasers anywhere. You can do all sorts of examples where you can emulate a mini sun, assume the floor is flat and level in a long distance area, take a far away light, right? Placing the light towards the camera, raising it and lower it from the floor. And then you can change the observer height and you can mimic the same effect. Now, if only we had another real world example where we could mimic this. Oh, wait. Our Flat Earth Netherlands brothers hooked us up. Right, so they have the top and the bottom limits mimicking the lower, the ground level and the horizon and the skybox. And the laser is going to be the sun. They're going to push it linearly away from the observer and it's going to appear to set. Right? It's going to obey the orthogonal and transverse lines. If you can imagine, it's going to obey the transverse lines as it obeys depth perception. It's going to obey the orthogonal lines as it's going to decrease in angular size proportionally right up to the horizon. And as it gets to the horizon, look, the lower bottom of it is being obstructed. This is not curved, this is flat, but we're losing it from the bottom due to the limits of our angular resolution limit and our position of the eye line closer to the lower limit than the top. Another real world perfect effect of limiting exactly what we're talking about here. Shout out to Flat Earth Netherland, man. This is one of my favorite Flat Earth sunset proofs, but I think it follows nicely on the actual explanation with the mathematical description of what we were talking about earlier and how this is exactly going to mimic both in forward sequence and reverse, how something would disappear bottom up on a flat surface with these perfectly mimicked flat lines, which is laid out with string. So you can't say the string is curved at this point because they did end up saying that warehouse was curved. That's how they got away with that one. So these strings are not curved, you know, come at me, bro, as they say. Same effect. Again, for the real world observation, here's what we're seeing. Nothing is setting. It's not rocketing backwards faster than the speed of sound, giving us the illusion of it setting. It's just moving away from you. I think there's one more cool animation I threw in here at the end. Although I do like that one. Oh, what a simple 3D, wonderful gift to show exactly what we're trying to demonstrate, right? Perfect. And again, if we take what we've learned and we apply it to real world situations, if we're trying to look into the horizon at a beach with all through the atmospheric deck of opacity through what is probably real world atmospheric refraction, which is, you know, different and has a differential proportionate with the density gradient, meaning so directly with temperature. So you're looking at all these different variables and you're saying, okay, now all these things that are definitely happening, we know that this is because of Earth curve, right? It's like, well, the famous Skunk Bay footage then would mean that Earth curve is wobbly as hell, right? It's all inconsistent. It's no, it's not. The Earth curve isn't changing. Atmospheric conditions at the ground are changing. And if you notice, the height and depth of these buildings are changing. They are thickening and shrinking. They are, what do you call them? Expanding and contracting, which you wouldn't expect to see, right? So if you're saying that, the height of this building is now the height of this tall, they're changing at all times. This is one day. The time scale is back from 2012, and we haven't even been, 20 minutes yet. This is inside of 2 hours. 2 hours, and the cameras, everything is all up everywhere. So based on the heat, based on the atmospheric opacity, based on everything, all of these atmospheric changes are wildly unpredictable. So when we're saying that we know that whenever we're missing the bottom of an object in real world, we know that it's Earth curve, is the most retarded statement I can think to make. Because we could also say equally, it could have been a mirage, it could have been refracted, it could have been a part of your angular resolution limit, it could have been, my God, literally, why wouldn't it have been the actual visual, loss of information at a horizon, at a level plane, due to the limits of your optics and the subtending of angles based on how you perceive? Why would that not be the first guess? Why would it be Earth curve? Anyway, going over that example, right? If you view the eye line at the horizon, sometimes you see an inverted reflection. Sometimes it pulls the distance object lower. Sometimes it pulls them higher. As we saw, it was unreliable. It was all over the place. From a 12-hour time lapse, how much the apparent shoreline changes. If you drew a line where you thought the horizon was at 8 o'clock, at 8 o'clock at night, it would be completely in a different position and it would have jumped all over the place. If we remember, because of the lensing refraction through many different layers, we saw all of these things change. If we were to put them all together, these were all at different heights. If you had a crafty glober over here, he would try to convince you that over here, when he showed the picture of Skunk Bay, he knows that the height from over here is, X, but this is much disappearance. So now we know this is how much Earth curve there is there, guys. And this is the sneaky bullshit they pull all the time without taking into account any of the stuff that we went over tonight. So I was trying to go over most of the things that we can explain and quantify and empirically sort of account for when we're missing information from an optic observation starting at the bottom up. I think we're just at an hour, and I think we're almost at the end. I think this is pretty much it. So again, what we're trying to explain are all of these observations based on optics. Now, Globers would tell you that some of these are because of Earth curve and some of these are tricks. Well, I'm just going to say that they're all done on a flat plane and they're all showing the same thing and they're all mimicking the same effect. We have bottom up obstruction, meaning we're losing information from the bottom because of the height of our eye line and the rate at which equal and unequal angles decrease. I think that's it. What do you guys think?
Bravo. Thank you, Shane.
Woo!
Woo!
That was good, dude. That was a good one.
Yeah, that was awesome, bro.
Play Reality, what up, man? I was gonna
Yeah,
I was gonna insert your Harry Sally, but I couldn't figure out a good way to organically shove it in there. But I was trying, dude.
No, it's all good. Hey, can I just throw in one thing? So, see where we come from this. So, the light is obviously bending, so it's traveling straighter for further on particular days. So when I show how we're getting a horizon that's definitely at closer to 3 miles, and then on another day we're having a horizon closer at 15 miles. When we have that horizon closer at 15 miles, the objects that are closer to 15 miles just get tiny. Like they're way smaller than. So when we have the horizon that's at 3 miles and everything's starting to disappear, we obviously have all those objects at only 3 miles away. So therefore they appear larger in our vision. But when the horizon's more like 15 miles away, obviously now those same objects are 15 miles away, so they're smaller, meaning that the angle to them has increased or decreased, whichever way that's meant to go. So that's where the angular resolution in that would kind of slightly differ in a way, would it not?
Should slide a different way than what I said.
No, not different than what you said. But so let's say when a horizon is created at 3 miles away, the angles to those objects would be different than a horizon at 15 miles away.
Yep.
From the same observer height, I'm talking, not from changing observer heights, from the same observer height.
Yeah, I think so.
Yeah. So yeah, I'm not too sure if I just explained myself properly. So I'm just sort of mentioning on how that distance will change, but everything will still behave in the way that perspective and angular resolution and that works, because those things will get smaller in the distance.
Proportionally, yeah.
Yeah,
So yeah, I think the point that I think I would try to make is that when they try to get you, when an object has a portion of itself above your eye line and a portion of itself below your eye line, it gets tricky because they will decrease at different rates, right? The top will decrease at a different rate than the bottom because of their position above and below your eye line. So a mountain in the distance is a great instance of that, because a certain amount of that is below your eye line, a certain amount, most of it is up top. So it'll increase vastly more quickly than, say, a 6-foot observer in a closer frame of reference. So people could be like, "Oh, how come this person is above the mountain when the mountain, that's Earth curve?" That's a crazy argument, I think.
Yeah. So then when we have, obviously, if the light is bending at the 3 mile mark, then the lowest angle that we have that can be resolved will be at 3 miles. And that, like, the lowest part of the ground or the surface, that angle is now at 3 miles. But if that moves to, say, 15 miles, now that lowest angle that we can possibly get to, where the light will reach, will be 15 miles away. So there'll be a slightly different angle there, but I'm gathering that because the light is now traveling further, we're actually able to see that lower point because the light is actually reaching it. Is that being explained right? Because there is a difference, there is a slight difference there, because we are definitely seeing different distances on different days. So there has to be a slight change in the angle.
Yeah, so a lot of it's changing. I mean, the distance to the horizon is based on, you can do the famous Rayleigh's criterion distance to the horizon based on, which, of course, wavelength diameter for the focal length of the eye. You could do the 6-foot observer height and distance to the horizon based on either a 6-foot observer or on the ball, and you could definitely get 2.999997 miles, so essentially 3 miles, right? Which
Yeah,
changes
I
an
think
object.
yeah, it seems to me like that whole Rayleigh's criterion thing is where like on those particular angles is what we got the globe from, because that's kind of like where they say the actual geometric horizon is for each different observer location. That would be the geometric horizon, but that changes.
Yep. That's why I
So
have a spreadsheet that really compares those two values together all the time, and you can do the geometric. All right, here, let's just look at it. It's right over here from my boy Amish. Right, let me put it up on my stream. Crap, I didn't have Discord shared. Let's do that. Discord. There we go. All right, cool. So literally you can have the geometric horizon being calculated over here, and then you have the optical horizon being calculated over here with the limits of optics, 6-foot observer using diameter, wavelength, and height, and the geometric horizon over here with the radius and the regular observer height, and you see they're exactly equal. So if you say plain reality were to argue that they built the globe limits based on optics, I would wholeheartedly agree with you.
yeah, that's awesome, man. Like really good work.
To how many degrees of accuracy?
8 decimals ish, I think.
Bingo. So they took a property of optics and they just called it Earth curve.
Which
Yeah.
property? Which wavelength, though?
The end of your resolution.
Can I ask a question? Like, I don't know how to raise my hand in here.
Oh yeah, you're good.
But that was a really okay.
you
That
guys-
was a super good presentation. There were a couple things in there I would like to have, like that demonstration of the sun on the angles, or maybe like the video where you zoom in and you actually can see it's not going behind the curve. Those would be really nice to have. Yeah, that was really good. Oh yeah, Morgan was this Globe Earther on Twitter was asking me to like send him an optics paper describing bottom up obstruction, and I was wondering if anybody here had one that I could share and just have on board. So I'm like making like now like a sheet, full of all this information. I'm trying to gather it. So if anybody asks me for anything, like I could just share it with them. So I'm kind of compiling that. So yeah, if anybody has like an optics paper or something, like that's what he was asking for, that talks about this, that'd be nice.
Oh yeah, we got a library of optics papers. Like here's a quick bibliography of the supporting optics papers. I think we have I don't know if I have a EtherCause file share with all just optics categorized out. Alan, can you hit me with a GitHub categorical search link or something?
Yeah, search.spaceaudits.net.
Are there papers that go over bottom-up obstruction? Because really in their world, they just look at it as, well, it's going over the curve, so why do they need to explain that?
Well, if you believe in hostile witnesses, then absolutely. Essentially, they have all sorts of papers, limits of optics. They have going over the Gaussian efficient, going over angular excess, where they predict amount of spherical excess based on the limits of your optics. They have perpetual 3D space, visual field versus perceptual space, meaning what you can see versus how it is linear. The use of Euclidean versus non-Euclidean as the best way to perceive orthogonal, 3D lines. I would say they're like vaguely supportive, mostly supportive, and indirectly supportive.
So indirectly, they're saying that what you're talking about is correct.
Yes.
But then just reifying it onto a ball.
Maybe, or maybe they'll talk about electrons or something, or atoms, and people will be like, whatever. And I'm like, what they mean is, they're honest intentions. They're trying to describe the phenomenon around them, and I agree with 2 of these points, right? So, hold on.
Nice.
I'll get the list.
Hey Shane, last Flat Earth Friday, were you awake when I talked to Jesse for a while?
Hell no. I heard Jesse was coming, and I put myself to bed. Or maybe he spoke one word and it put me to sleep immediately. One of those 2 things happened.
Well, I just talked for a while about the work he's done, and I basically was telling him I think that he's perfectly finding out and showing how they made the globe out of how we see. But of course, he keeps saying ball, 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 Earth. But that drop in the distance isn't because it's going over a curve. It's just because of perspective. But yeah, I talked to him for a while and just was like, look, man, you have good intentions. I believe you do, but we don't live on a sphere anyway.
That's true. That was another question I was going to ask. Like, could this be Jesse's work? Basically, he uses theodolite and said, "Hey, this mountain is shorter than what it should be, based on like distance and yada yada." So I was like asking if he like incorporated anything from bottom up obstruction, and I understand his answer about why he was saying like he wouldn't have to. And I was like, okay, I was just curious, but I was wondering if there was any more geometry on that, like why the mountain would look shorter than it actually is, and if that could explain why he's seeing what he's seeing.
Well, I mean, the amount of the mountain that's above the theodolite's eye line will increase much quicker than the amount that's below, so it will give us, say, a false perception of the amount that's missing from the bottom. But the truer measure will always be from the top because there'll be way less obstruction and mystery and refraction and other conditions at the at the top than there is the bottom. And that's why our argument is always, hey, based on the Earth curve metrics and 8 inches per mile squared, the top of that mountain is visible way too much. And they're like, well, no, the bottom because of this, and it's like, no, that's retarded. You like the whole argument because they can hide in the weeds down there at the horizon level where there's gray area, atmospheric opacity, fluctuating conditions like crazy. Up top, you can't really hide. Like it's very predictable, right? And then you're left with the diffraction limit, which is measurable, quantifiable, and empirical, and you're consistent, and then you're not depending on atmospheric refraction, which is variable. Because they like to hide in that variable. They're like, oh, you see how it wobbled? That's Earth curve. See how it went up? Earth curve there too. Oh, more Earth curve. Swap it up. Crazy. And there's nothing that we can do to like mathematically combat it because these people will mathematically reify themselves right into reality. See Alan's first presentation name, How Math Became Reality.
Right.
So what do you think is the best? Like, so one of my conclusions with talking to Jesse was, first of all, I told him I want to start and do the math from scratch myself. But for this case, like I was like, okay, so on your videos, like the numbers don't match up with your spreadsheet. And he's like, yeah, that's because it's better for me to use two hands. And so, and I was like, well, you need to get like a camera holder. And then I was like, okay, so you need to make a video and you like give me the numbers, from the actual video, and like show that you're using these numbers because like on the spreadsheet, those numbers are different than on his video. So anyway, he says he's going to get a camera holder. And then whenever he gives me those videos, I said I want to get my own mathematicians to look at it. And so, that's kind of where we're going to go from there. Nice. So if y'all know any mathematicians, I don't trust his math either. Okay, so I just want to start from scratch.
My recommendation is stop talking to Jesse, but each his own. I had to learn tough lessons too.
I know, but still, like, he claims it's the end-all, be-all proving the globe. So I just want to, I don't know. I want to be able to give him a good answer.
No, I know you're a better person than me.
Didn't you get enough to answer him out of our discussion the other night, Taylor?
I know, right? Yeah, out of our discussion, absolutely. And that's actually, okay, I think that was Stone talking. And yes, your points are the ones that I brought up to him in that space. One of the points from that video was like how the numbers don't match up. And then a couple other points about how you can't even use theodolites, at this distance, and things like that. So I did bring up these points to him, but I don't know. One of the ones that kind of stuck was just that the video doesn't match up with his spreadsheet. So yeah, I did get a lot out of talking to you, but I don't know. I just want to follow up with him and like just put this whole Jesse thing to rest because multiple people are invoking his results,
They all will keep doing it no matter what you say about it, though. He's like the end all. So I had to learn the tough lesson too. Like Witsit told me not. He was like, "Dude, he's the worst," and I'm like, "I don't know, man. He seems super nice and genuine. Like maybe you're an idiot, Witsit." Like that's what I said. I was like, "Maybe you're wrong, Witsit. Maybe you're a fucking retard, and I know better than you." And then 6 months later, I couldn't have been more wrong. Well, I mean, I didn't really, but I was like, "No, I'm confident that you're wrong about this, buddy." And he was like confident to let me make my own mistakes, right? Which is what I
So
can
where
do.
do you think the bending of light will come into this as well? Because it does seem that the light is generally refracting upwards. And so that would mean that obviously the light is also only getting to us from certain sections of things in distance. So where do you think that comes into it? Because I would be suggesting that wherever that light is actually originally making contact, that will also drop down to our horizon because we only see it. So that will also become right down onto our horizon.
Personally, I see the act of engaging them quantified methods used for measuring refraction, you'll find that they are expressed in terms of percentage of Earth curvature. So in even invoking that particular quantification, that method of describing refraction, we are snared by their method of measurement, by their unit of choice. Can you see how that works against us from point one as soon as we engage in that?
Units of refraction are derived from the globe ratio, or from a ratio of the radius of the globe.
Yeah, the refractive value is a ratio against a SUMED Earth curvature.
Yeah, but that's all just reified, basically, really, isn't it? But
That is the
what I'm
term.
sort of getting at
That
is
is
that
the term.
we do, yeah, but we do know that the light is bending. I mean, all the laser lights that get shown bending upwards do demonstrate and show us that the light will bend, but it tends to be bending upwards, not downwards around a curve, to make things appear to be risen
Quite.
up. So we are getting some form of bending of the light.
I don't believe in the bending of the light personally and prospectively. I don't think it's a thing that happens. I think that when you're trying to observe an orthographic godlike view of a light ray that no one's ever seen, I think that it's a crazy way to go about it. Like, so it gets into light traveling. If you have a light ray that is traveling physically from one to the other, is it really traveling though, or is it already there? Is it in a medium? Is a whole different other discussion, right? So that's why I don't ever really get into like when Jesse's draws his little line. Like, wait, if I draw this light ray and the path of this light ray is, it's like, no. That's not how I think any of it works at all. So I can't possibly make a best guess judgment on what I think is happening and based on those things, right? That's just me.
Hey,
Yeah.
in the case of like Balaton in Hungary, with the FE core test. Now, I was watching that live when they were doing it, and well, it was several days. It was like a whole week, and in that process, we were getting communications back from the team that like if they had left, because it was a very strong laser. Okay, so it was like a $50,000 laser, and in the process of using that laser, because it was so cold, especially, and it was dry, so it wasn't a lot, basically no humidity. But in the process of using the laser, they saw the beam actually. The longer they left the laser on, it would actually curve the light up. So it's as if it was cooking the air that it was passing through, and that heat was causing it to bounce up. So they could only use it in spurts. They couldn't actually leave the device on.
Right. So then you think that with the lasers, that then clearly then the longer the laser is on, then more heat's created, and then
Well,
obviously that heat creates a
not all
different
lasers.
density right where the laser is.
Yeah, so I guess the point of me bringing it up is that it's never talked about, and I'm not saying this happens with all lasers, but it's something to consider that laser light is not necessarily a flashlight or ambient light or point source or anything like that. Like laser light is a particular type of light, and there's different types of lasers, so you can't just use a blanket statement of why this thing is going up or that thing is going down or whatever. You kind of have to know the particulars of what's taking place. So now that you know that, it's something you can think about or consider.
Right. Yeah. So the idea of how the horizon is 100% definitely changing distances from viewing it from the same viewer height. And this is what made me start to think that there must be a bending of the light, because otherwise, how come on one day I can see a horizon at 3 miles and then another day, or even just 4 hours later, now that horizon's at 15 miles?
Yeah. Well, I
And it
would say
goes everywhere
clarity.
in between that.
I would say clarity in the clearest, most predictable, homogeneous conditions. You get clarity. That's when you see the furthest, right? Because the more refraction you have, the more variation you have in temperature or climate, you're going to get obstruction. You're going to get particulate. You're going to get, haze or whatever. And it's the clearest days with the most similar temperature and similar condition you can see the furthest.
Yes, I agree and disagree, because there are still very clear days where the horizon will be close. You can have inferior mirage days where there's just beautiful, totally clear. Everything looks picture perfect, but you have a horizon that's, say only 3 miles away. And then I can have a picture clear day where the horizon might be 6 miles away, and then another picture clear day where it might be 15 or 12 miles away. And then you can have hazy days or distorted days with it all in between there as well. So I can have extreme distortion days where we have a really far horizon, and then I can have a clear day where we have a really far horizon, or have a clear day where it's really close, and then a distorted day where it's really close.
Yeah.
So there's got to be something happening to the light to create this difference in distance.
Well, okay, so your average height is what? Are you considering all these different factors?
Well, my average height is at 20 feet. So, excuse me.
Well, that
So
gives you a lot of
mine
headroom that's a lot of headroom for 6 miles. That's more than enough you would need for 6 miles. So if you're seeing
Yeah.
less than that, it's probably because of the distortions I was speaking about.
Well, what do you guys think about the top-down argument? Has anyone ever heard that one before? Has anyone ever looked at the building?
Yeah, that's good. I like it.
Yeah, that was a great. I like that a lot, actually.
Right.
I'd never seen that before.
Or if I just curve the top of the building, or maybe it's a function of optics both ways, and what we're saying on the horizon is 100% true. It's like, you ever seen a tall building? Yeah, Earth is flat, bro.
By the way, are you still live? You guys still live?
Yeah, so any more questions, or wrap this up? I was trying to keep it under an hour, but I think I made it just about an hour. But trying to keep it short, presentation-wise, so we don't go into 2-hour bangers. Tomorrow is the debate on optics and Earth curve with some random poor guy on Twitter. Which would be fun.
Peace be upon him.
Jeranism. He's probably not going to watch any of this. If anyone also asks, I also became an expert on bridges. So we'll see how that goes. That'll be fun.
Nice.
And then after that, I think Alan is debating right after that. So we'll have a twofer. Tomorrow I'm debating, and Alan will run a nice after show or live stream in here. And then Thursday, Alan will debate, and I'll run a nice live stream after show in here. And we'll do the reverse, and then it'll be Flat Earth Friday again, I think.
Yes.
And then it looks like
Go ahead.
Sorry, go.
You're good. Go ahead.
I was just going to say, sorry. Yeah, it looks like Brian's actually trying to set up a debate with me and Brian, and then Ruhif, and apparently maybe Mordwan.
There you go. Ruhu's kind of my favorite Glober, but Mordwan's kind of.
I wanted to thank you, Shane, just for putting my Lake Pontchartrain video in the background of your podcast. That's super cool.
I was like, yes, this is my favorite picture ever.
Yeah, those videos
It's
were
awesome, dude.
At one point,
I'm
had
happy
the
we
drone.
put that Lake Pontchartrain Bridge to rest, man. There's so many reasons why. Just put to rest completely. They better not ever post that thing again.
Oh no, it's like I'm lying in wait like a predator now, and I have this like poison dart, and I'm just waiting for the next Glober to be like, oh look, it's curved. Pounce on him, it's gonna be great.
Oh, that's great, dude.
Can
yeah,
can you
cool
provide a
video.
link to your?
Glad you made
Sorry,
it.
can you provide a link to your video?
To Taylor's thing, I think it's.
It's on my Twitter. If you DM me on Twitter, it's TAYLERV__, like Taylor V __. And then I could DM it to you.
All right, cool, thanks.
Yeah, if you scroll up to 9 a.m. or 9 p.m., Riggs linked her Twitter up there, so you can get it there if you need a link.
Nice. She's a G.
I was gonna say, thanks for the great work, guys. This was excellent.
Thanks everyone for turning up, coming out, and we'll probably hang out for a little bit after this, but closing out the stream.
Yep, same. I'm going to close mine out. So check Shane's debate out tomorrow. We'll be doing a live watch party tomorrow. So I think it starts at what time, Shane?
Crap, I gotta ask Jaron. What time does it usually start? Is that time?
8 and/or 9. So anyway,
one of those.
Check in with us tomorrow. We'll be watching that on the Discord, doing a live watch party, and then the following day I'll be debating Mordwand on QED. So stay tuned for that. And then Saturday, well, first Friday will be Flat Earth Friday episode 116, and then after that, I have a presentation on Saturday at 2 p.m. The Steel Man of Relativity, and then the subsequent dismantling of it.
Busy schedule for the Ether Cost Boys this week, it looks like.
Yes, sir. All right. Have a good night, everyone. Catch you guys tomorrow.